Welcome to this short demonstration of what we call an Attwood pulley. This is a demonstration actually of Newton's second law. And the way this works is we have a small mass that's hanging at the bottom here. And we have a larger mass that is, of course, on wheels. We might assume that it's frictionless, in which the coefficient of friction would be 0. Or we could assign a coefficient of friction to make the problem a little bit tougher. Now, so what we have is the smaller mass, it falls due to the force of gravity. It pulls this larger mass, and we can change the magnitude of that larger mass and determine the acceleration of the system by using Newton's second law, which is A is equal to net force divided by mass. In this case, the net force is going to be the force of gravity acting on the small mass minus the frictional force. Now, if there's a 0 coefficient of friction, then the frictional force is 0. But here we have mu times the mass of the large object times gravity. That will give us the force of friction. So the applied force due to gravity minus the frictional force, and then we take that net force, which is on the top, and divide it by the total mass of the system. And that should give us our acceleration. And whether we do this in this applet, which works perfectly, of course, because there's no experimental error, or we do it in real life, which we have a lab set up on WebCT, and you can watch that. And the human component makes for a small amount of error, but makes it more real. So what we can do is set these data, and I'm going to start with the hanging mass of 1.0 grams. And I'm going to start with a large mass, that is the mass of the wagon at the top. I'm just going to say let's let it be equal to 0. Therefore there is essentially no mass there, just to see what happens. And what we find is we use the equation acceleration is equal to 2d over t, or in this case they've written it as 2s over t squared. And of course when we start this, we find that the mass went 0.5 meters, it fell 0.5 meters, and it took 0.319 seconds. When we use that equation to calculate the acceleration, assuming that the initial velocity was 0, we get 9.81 meters per second squared. So the small mass falls like a rock, okay? Because there's nothing holding it back, so it falls due to the acceleration of gravity. Well, when we reset, we can change that mass of the wagon to whatever we want. Let's try 1.0 grams. Now what we've done here is we've increased the total mass of the system. We haven't changed the mass of the little guy here. It's still 1 gram, and it's still going to have the same force acting on it. What we've done, however, is we've added a large m. We've added 1 gram for large m, 1 gram for small m. Now we have 2 grams on the bottom. By taking the same net force, dividing by 2 instead of 1, we should have our acceleration. All right, it's called an inverse relationship. As the mass of the system gets bigger, the acceleration of the system gets smaller. So let's just run that, and we see that in this case it took a little bit longer for the mass to fall because it's pulling the large mass as well. So the same net force is acting on a larger mass, and therefore we get, notice, half the acceleration. Half of 9.81 is 4.905. So this seems to work. And we can do all kinds of different experiments using both the two masses. We could, in fact, as a problem, I could say, all right, let the mass of the small object be 5 grams, and let the mass of the large one be 14.7 grams. And then, of course, you could then predict what the total acceleration is going to be. And we could give you a little bit of time to do that, and then we could say, okay, run start, see what happens. And of course, with these particular settings, it would be 2.49 meters per second squared. And we could change all of these parameters to whatever we want. We could even add friction as another force. So we could reset this and say, let the coefficient of friction be 0.2. Therefore, we have, of course, 5 grams pulling, 15 grams is stationary in large mass. Then we let it run, and we start, and it goes quite a bit slower. In fact, 1/10 of the acceleration of gravity. We could even maybe play a trick on you and say let's let the coefficient of friction be 0.9. Now I'm thinking that maybe in this case when we press start, notice what happens. It says too much friction. That's because the frictional force down at the bottom here, mu times the large mass times g, is larger than the applied force, so therefore this doesn't move. And that's a good example there. So hopefully this is a good explanation of Newton's second law and the Attwood pulley itself. Notice that we can, by adjusting the coefficient of friction, we can actually we could frame a question to say what is the maximum coefficient of friction or the minimum coefficient of friction required to allow the pulley to move with with the minimum acceleration. And so by making it 0.34 and then we press start, nothing happens because there's too much friction. If we make it 0.334, all right, 0.333 actually, and we click start, then we get a little bit of acceleration. It's very, very slow. And eventually we'll find that this acceleration is going to be something around 0.002. We won't wait for that, but what we'll do is reset and set it at 0.334. We'll just change that number by 1, and we'll notice now that there's too much friction here. And so we found that between the coefficients of 0.333 and 0.334, that's when motion seemed to stop, and therefore, or start if you're going the other way. And that would be a good question. That would be the answer you get on a test. Now we did it by trial and error, but you could solve the equation out of the bottom here for making acceleration equal to 0 and then solve for mu, and that would give you your same answer, 0.333.